The National Electrical Code, or NEC, does not explicitly address chemical grounds, but it does provide guidance on grounding for sensitive equipment. Section 250.119 requires that all non-current carrying metal parts of equipment, enclosures, and raceways must be grounded. However, this section also allows for exceptions where it is necessary to isolate a circuit to prevent noise or interference. Section 250.24 requires that the grounding system be connected to a single point near the service entrance. However, it allows for the use of multiple grounding electrodes to improve the grounding effectiveness. IEEE Standard 1100-2019, which is the recommended practice for powering and grounding sensitive electronic equipment, provides detailed guidance on designing and implementing grounding systems for sensitive electronic equipment. It recommends using a separate grounding system for sensitive equipment to minimize noise and interference. One option to isolate the electron microscope from the main ground bus is to use an isolation transformer. This transformer provides electrical isolation between the microscope and the rest of the power system, reducing noise and interference. Chemical grounds are not designed to handle electrostatic discharge, or ESD. If ESD is a concern, additional measures should be taken to protect the equipment. Removing the bonding jumper from the main ground bus creates the potential for a shock hazard. Ensure that the system is properly designed and installed to meet safety requirements. While the NEC does not explicitly address chemical grounds, it allows for isolating circuits to prevent noise and interference. IEEE Standard 1100-2019 provides detailed guidance on designing and implementing grounding systems for sensitive electronic equipment. Using an isolation transformer is one option to isolate the electron microscope from the main ground bus and reduce noise and interference. It is important to consider safety and ESD protection when designing and implementing any grounding system. It is always advisable to consult with a qualified electrical engineer to ensure that the grounding system meets all applicable codes and standards and is designed to address the specific needs of the equipment and facility. Grounding systems are crucial for electrical safety and equipment protection. Understanding the different types of grounding systems and their applications is essential for electrical engineers, technicians, and anyone working with electrical equipment. The NEC provides a comprehensive set of rules and regulations for grounding electrical systems. Following these rules is critical for ensuring the safety of people and property. One of the key principles of grounding is to provide a low impedance path for fault current to flow back to the source. This allows the overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and energize the circuit, preventing electrical shock and fire hazards. There are several types of grounding systems, including, firstly, equipment grounding systems which connect the non-current carrying metal parts of equipment to ground. This provides a path for fault current to flow back to the source, tripping the overcurrent protection device. Secondly, system grounding systems which connect the neutral point of a power system to ground. This helps to stabilize the voltage and provides a path for ground fault current to flow. Thirdly, electrode grounding systems which use grounding electrodes, such as ground rods or ground plates, to connect the grounding system to the earth. This provides a lower impedance path for fault current to flow to the earth. In addition to the NEC, there are other standards and guidelines that provide information on grounding, such as IEEE Standard 1100-2019. This standard provides detailed guidance on designing and implementing grounding systems for sensitive electronic equipment. One of the key recommendations of IEEE Standard 1100-2019 is to use a separate grounding system for sensitive equipment to minimize noise and interference. This can be achieved by using an isolated ground system, where the grounding conductor for the sensitive equipment is isolated from the main built-in grounding system. Another important consideration when designing grounding systems is to minimize ground loops. Ground loops occur when there are multiple paths for ground current to flow, which can create noise and interference. To minimize ground loops, it is important to use a single point grounding system, where all grounding conductors are connected to a single point. When working with electrical equipment, it is important to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them. It is also important to be aware of the potential hazards of electrical shock and arc flash. Electrical shock can occur when a person comes into contact with a live electrical conductor. Arc flash is a dangerous electrical explosion that can cause severe burns and other injuries. To prevent electrical shock and arc flash, it is important to follow all safety procedures and use appropriate personal protective equipment. Here are some additional details on specific sections and concepts related to grounding. Firstly, grounding electrode system, which according to NEC section 250.50, all grounding electrodes that are present at each building or structure served shall be bonded together to form the grounding electrode system. Secondly, grounding electrode conductor, which according to NEC section 250.62, a grounding electrode conductor shall be used to connect the grounding electrode or electrodes to the equipment grounding conductor, the service equipment enclosure, the grounded conductor of the system at the service, the disconnecting means, or to the grounding bus of a separately derived system. Thirdly, equipment grounding conductor, which according to NEC section 250.118, types of equipment grounding conductors. For example, a wire or rigid metal conduit. Fourthly, bonding, which according to NEC section 250.92, bonding of services equipment. The non-current carrying metal parts of equipment shall be effectively bonded together. Fifthly, separately derived systems, which according to NEC section 250.30, grounding requirements for separately derived systems such as generators or transformers. Sixthly, impedance grounding, which according to NEC section 250.36, high impedance grounded neutral systems. Seventhly, surge protection, which according to NEC section 280, surge arresters and surge protective devices, or SPDs. Eighthly, sensitive electronic equipment, which may require dedicated grounding or isolation techniques as mentioned in IEEE 1100. Grounding is a complex topic, and it is important to consult with a qualified electrical engineer to ensure that your grounding system is properly designed and installed. Improper grounding can lead to electrical shock, fire hazards, and equipment damage. The information provided is for general guidance only and should not be considered a substitute for professional electrical engineering advice. Understanding NEC tables such as 250.122 for sizing equipment grounding conductors, or Table 250.66 for sizing grounding electrode conductors for alternating current systems is important. The NEC is updated regularly, typically every 3 years, so it is essential to use the latest edition of the code. State and local electrical codes may also have additional requirements. Always consult with local authorities having jurisdiction or ODGs to ensure compliance with all applicable codes and regulations. When dealing with sensitive electronic equipment, it's crucial to be aware of the potential for electromagnetic interference, or EMI. Proper grounding techniques can help to minimize EMI and ensure the reliable operation of the equipment. Shielded cables, filters, and other mitigation techniques may also be necessary. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections can corrode over time, which can increase resistance and reduce the effectiveness of the grounding system. Visual inspections, resistance measurements, and other tests can help to identify potential problems. Chemical ground rods, while not explicitly addressed in the NEC, are sometimes used to improve grounding in areas with poor soil conductivity. However, they should be used with caution and installed in accordance with the manufacturer's instructions and any applicable local codes. Always consider the environmental impact of chemical ground rods and take steps to minimize any potential contamination. In summary, proper grounding is essential for electrical safety and equipment protection. Following the NEC and other applicable standards, consulting with qualified professionals, and performing regular maintenance are all crucial for ensuring a safe and reliable electrical system. Ignoring grounding requirements can have serious consequences, including electrical shock, fire hazards, and equipment damage. Take the time to understand the importance of grounding and ensure that your electrical systems are properly grounded. The size of the grounding electrode conductor is typically based on the size of the service entrance conductors. See NEC Table 250.66 for specific sizing requirements. The equipment grounding conductor size is typically based on the rating of the overcurrent protection device protecting the circuit. See NEC Table 250.122 for specific sizing requirements. Grounding electrodes must be installed in accordance with NEC Section 250.53. This section specifies the minimum depth and spacing requirements for grounding electrodes. The resistance of the grounding system should be as low as possible. A resistance of 25 ohms or less is generally considered acceptable. Ground testing can be performed to measure the resistance of the grounding system. Regular ground testing is recommended to ensure that the grounding system is functioning properly. If the ground resistance is too high, additional grounding electrodes may be required. The use of ground enhancers can also help to reduce ground resistance. Ground enhancers are materials that are designed to improve the conductivity of the soil. These materials can be used to improve the effectiveness of grounding electrodes. When installing grounding electrodes, it is important to avoid underground utilities. Call before you dig to locate any underground utilities before installing grounding electrodes. Damaging underground utilities can be dangerous and costly. Always follow safe work practices when working with electrical equipment. Wear appropriate personal protective equipment and energize circuits before working on them. Grounding is a critical aspect of electrical safety and should not be taken lightly. Ensure that your electrical systems are properly grounded to protect people and property. Remember to always consult the latest edition of the NEC and any applicable local codes. Also, consult with a qualified electrical engineer for any questions or concerns regarding grounding. The NEC provides minimum requirements for grounding. Additional grounding measures may be necessary to protect sensitive electronic equipment. IEEE Standard 1100 provides detailed guidance on grounding sensitive electronic equipment. Consider using an isolation transformer to isolate sensitive electronic equipment from the main power system. Isolation transformers can help to reduce noise and interference. Proper bonding is essential for a safe and effective grounding system. All metal parts of the electrical system should be properly bonded together. Use appropriate bonding connectors and techniques. Regularly inspect and maintain the grounding system. Replace any corroded or damaged components. Grounding is an ongoing process. Stay informed about the latest grounding techniques and technologies. Attend training courses and workshops to improve your knowledge of grounding. The NEC is constantly evolving. Stay up to date on the latest code changes. Grounding is a complex topic. Don't hesitate to ask for help from a qualified electrical engineer. They can provide expert advice and guidance on grounding. The goal of grounding is to provide a safe and reliable electrical system. Proper grounding can help to prevent electrical shock, fire hazards, and equipment damage. Take the time to learn about grounding and ensure that your electrical systems are properly grounded. It is also important to understand the difference between grounding and bonding. Grounding is the connection of the electrical system to the earth. Bonding is the connection of metal parts of the electrical system together. Both grounding and bonding are essential for electrical safety. Bonding ensures that all metal parts of the electrical system are at the same potential. This helps to prevent electrical shock. Grounding provides a path for fault current to flow back to the source. This allows the overcurrent protection devices to trip and energize the circuit. In addition to grounding and bonding, surge protection is also important. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes or other electrical disturbances. SPD divert the surge current to ground, protecting the equipment from damage. There are different types of SPD. The type of SPD that is required depends on the application. It is important to select the appropriate SPD for the application. SPD should be installed in accordance with NEC Article 280. SPT should be installed at the service entrance and at branch circuits. Regular testing of SPT is recommended. SPT can degrade over time. Testing can ensure that the SPT are functioning properly. When installing grounding systems, it is important to consider the soil conditions. Soil conditions can affect the resistance of the grounding system. Soil with high moisture content is more conductive than dry soil. Soil with high salt content is also more conductive. The type of soil can also affect the resistance of the grounding system. Sandy soil is less conductive than clay soil. If the soil conditions are poor, additional grounding electrodes may be required. The use of ground enhancers can also help to improve the conductivity of the soil. It is also important to consider the corrosion potential of the soil. Corrosive soil can damage grounding electrodes. If the soil is corrosive, corrosion-resistant grounding electrodes should be used. Copper-clad steel grounding electrodes are a good option for corrosive soils. Stainless steel grounding electrodes are also a good option. In addition to soil conditions, the location of the grounding electrodes is also important. Grounding electrodes should be located as close as possible to the equipment that they are protecting. Grounding electrodes should also be located away from underground utilities. Grounding electrodes should be installed in accordance with NEC section 250.53. This section specifies the minimum depth and spacing requirements for grounding electrodes. When working with grounding systems, it is important to follow all safety precautions. Wear appropriate personal protective equipment and energize circuits before working on them. Grounding is a critical aspect of electrical safety and should not be taken lightly. Ensure that your electrical systems are properly grounded to protect people and property.